All right, good morning. And this is lesson 3 in electricity, and we are talking about parallel circuits today. All right, so today we're going to do parallel circuits. They're just a little different than series. They're a little bit trickier, but they're really not that hard. The tricky part is when we combine them. That'll be next week. All right, so parallel circuits. Parallel circuits kind of look like a ladder because they have several rungs. They're not one single series or one single circle like a series was. They're like ladder rungs. So a parallel circuit is when the electrical devices are connected across the same voltage. So the ladder rungs, if you will, each feel the same voltage from the battery. So here's what they look like. So you have your battery here, and that battery is directly connected. If you were to draw a line, you can draw a connection directly to each of these 3 resistors. And there could be 2 rungs, there could be 100 rungs, but that battery is going directly to each of these devices. There's no device in between them. So you can draw a direct line. So this would be a parallel circuit. And like I said, it kind of looks like a ladder because you have these rungs. Now, the interesting thing to note is that the current that flows out of here, if you think of it like water, that water flow, that electricity flow, when it gets to this junction, some of that flow goes straight and some of it turns and goes into this resistor. Then when it gets to the next junction, some of that one breaks and switches, and some goes here and some goes here. So that total current is split up between each of these rungs. Like I said, think of it like water. If this is 100 gallons per minute, 50 of it might go this way. That means the other 50 has to go here, and then maybe these split in 25 and 25. And that all depends on what these values are for these resistors. So the first thing, like I mentioned, is that the voltage is constant across each rung. So if this is 24 volts, then this resistor feels 24 volts, this one feels 24 volts, and this one feels 24 volts. The voltage is the same across each rung. Second thing, which I was just talking about, is that the current adds up to the total current. The current in each of these rungs, so whatever is here, whatever is here, whatever is here. If this is 10, 20, and 30 flowing through each of these, you just simply add 10 plus 20 plus 30, so you'd have 60 would be your total that's flowing through the circuit. So where parallel circuits get a little funky is figuring out what the total resistance was. In series, it was super easy because all you did was just add them up. Well, you kind of add them, but you add them a little differently. So to find out the total resistance, what you have to do is the total resistance is the inverse. So 1 over the total resistance is the sum of all of the resistances inverted. So 1 over, so let's just make up some numbers real quick. Like I said, 10, 20, 30. Let's say if that's what the resistances are. So it'll be 1 over 10 plus 1 over 20 plus 1 over 30. We're going to do an example problem so you see how this works. Don't worry about adding fractions. Simply put it in your calculator that way. Let it do a decimal, and then you'll invert it. But we'll do an example problem so you can see how that works. So, example problem. So you got a circuit with 3 resistors, and they're connected in parallel with a 24-volt battery. So the question is, find the total current and find the current through each of the resistors. First thing, draw a picture. So there's our picture. We got our battery here, and it says up here that it was 24 volts. And then we got each of our resistors, and we'll label them since they gave us our values. So we know our total voltage. And the thing that's nice about parallel is that total voltage is the same across each of these branches. The first thing it wants is the total current. Well, if we know total voltage and we want total current, we need total resistance. So we go to that equation. Like I said, so this is how this works. So simply write it, 1 over your total resistance is equal to 1 over each of your values. And if there's more rungs, you just keep adding them. So 1 over 250 plus 1 over 150 plus 1 over 350. You add all of them up. And like I said, just do it with your calculator. Don't worry about it. So for instance, when I did this, again, leave the 1 over RT just like it is and put this in my calculator, and my calculator gave me 0.0135. Now, that really doesn't mean anything yet, because since this is on the bottom, you have to invert this. So what you do is you do 1 divided by this number, and that'll invert it, that'll flip it over. So when you do that, you get 73.9 ohms. That is your total resistance. All 3 of these added up is going to give you a total of 73.9 ohms because they're in parallel. So now you know that, and we know our total voltage. We use our V equals IR equation, and this is the V equals IR just rearranged. And we do 24 divided by 73.9, and we get our current. Now remember, that is our total current. That's the current that's flowing out of the battery. But because current splits, the current through each of these branches is going to be different. So the question was, what's the current through each resistor? Well, using our V equals IR equation and rearranging it, so using this equation, we can do it for each of them. So the current going through 1, the current going through 2, and the current going through 3, we can plug it into each of these, and we can solve for the current flowing through each device. And since all the currents have to add up to the total current, it's best to always double check your answer. So once we got all this, we add them up just to make sure. And sure enough, we get 3.25 or 0.325 amps as our total current. Okay, so here's one for you to try. So go ahead and try this one. First thing you might ask yourself is, what is EMF? Well, EMF is electromotive force. And if you think about it, that's what's pumping everything through. So that is the voltage. So it's asking you, what is the total voltage or the voltage of the battery? So we need to draw ourselves a little picture. So here's my picture I drew. I stood it up so it kind of looks more like ladder rungs. So we got our total voltage down here. And we got resistor 1, resistor 2, resistor 3. It doesn't matter which order you put these in. It really doesn't. So you could have done 1, 2, and 3. You could have done 1, 3, 2. It doesn't matter as long as they're all in parallel. So first thing we need to do, since it wants the total voltage and it gave us the total current, then we need total resistance again. So again, go through that little process where you add them all up and then do the inverse thing. When you do that, you should have gotten 16.3. If you didn't get that, double check it. Make sure you add all those fractions up first and then invert it. So once you have that, use the V equals IR equation to find your total voltage. So then it says find the current through each of the resistors. So just like we did on the previous problem, use the V equals IR equation, and I just rearranged it. So current is equal to voltage over resistance. And so we have, just plug them all in, and we get the current through each of them. And they should all be labeled with amps, but I forgot to do that. And then, like always, it's always a good idea to double check. So add them all up and make sure they all add up to 1.8 amps. And if we go back up here and check, our total was 1.8. So everything checks out. So there should be a parallel circuits worksheet in the classroom section. So go ahead and give that a shot, and we will talk to you later.